Okay, so we did merge sort. We showed how merge sort works, and then we analyzed its running time, and then we got at this recurrence. Okay, so this tells us that the running time of merge sort for sorting a list of size n is twice the running time of merge sort on a list of size n over 2, plus some overhead for merging the two sorted halves of the list. This overhead in this case, in the case of merge sort, it's linear. Okay, so taking two lists of size n over 2 to merge them is going to take a time that is linear in the size of the input. Now, and we said that for the base case, when we have a list of size 1, I have a constant amount of work to do. And as we said, this is not the type of function, explicit function, that allows us to understand the running time. I cannot easily plot this, or I cannot easily imagine how fast or slow this is going to grow. So the question is, how do we go from this to some explicit function? How do we get from this to the function that the running time of merge sort is really O of n log n? So dealing with recurrences in general, this is a recurrence that we are seeing for merge sort, but recurrences are not only for merge sort or for these kind of algorithms. Recurrences are a very broad mathematical tool for describing functions, right? So sometimes we describe the function explicitly. We say f of n is 2n. But sometimes we describe a function in this kind of form. We say f of n equals f of n minus 1 plus f of n minus 2. Right? So we describe the function in a recursive way or in a recurrence rather than in an explicit form. But again, as I said, we would like to understand what this function is so that we understand how fast or slow the merge sort is. Fortunately for us, the algorithms that we are going to see that are going to do divide and conquer have this form of a recurrence where we take a problem, we divide it into two subproblems, each of equal size, n over 2, and we solve two of the subproblems, or a certain number of the subproblems, plus some time for the merging process. When we have a recurrence of this, the nice thing about these type of recurrences is that there is already a mathematical tool that will allow us to go from here to an explicit function very simple, in a very simple manner. Okay? And that mathematical tool is called the Master Theorem. And this brings us to the Master Theorem, which is written here. So Master Theorem applies to recurrences of this form. What is this form? How do we relate it to algorithms? Again, think about an algorithm that I want to solve a problem of size n. I divide the problem into b subproblems, each of size n over b. I divide the problem into b subproblems, each of size n over b of equal size. I solve a of them. Okay, so a cannot be greater than b, for example, because I'm already dividing the problem into b subproblems. I can solve 1, 2, 3, 4, or all b of them. Plus, I have some time f of n for the merger, for merging the subproblem, the solutions of subproblems. In addition, I have also constant time for dealing with the simplest cases or the base case. So for these general forms of a recurrence, I have the Master Theorem. Notice here that I'm saying a is greater than or equal to 1, b is greater than or equal to 2, c is greater than 0. These are not something to memorize. These should be values that make sense. Remember that I'm saying a is the number of subproblems that I solve. In the case of merge sort, I'm solving both of the subproblems. Here I'm saying in general, I'm solving a certain number of subproblems. What type of an algorithm, what kind of an algorithm, and what kind of a problem would it be if I'm solving 0 subproblems? I divide the problem into 2 subproblems and I solve none of them. That is a useless algorithm. This is why a has to be at least 1. Okay? So you don't need to memorize that a is greater than or equal to 1. It should make sense and should be natural for you to think about it. Second thing is b. We need to divide the problem into subproblems. If b is not greater than or equal to 2, the only other option is that b equal 1. I am taking the big problem, I'm dividing it into one big problem, and I keep dividing it into one big problem. What type of a divide and conquer is that? Of course, we have to divide it into at least 2 subproblems. 2 is not a magic number. You can divide the problem into 4 subproblems. The merge sort, you could have taken the original list and divided it into 4 sub-lists of equal size. You could have taken the original list and divided it into 100 sublists and repeat the same process. Okay? But here, B is the number of sub-problems that we divide the original problem into. So it has to be at least 2. We have to divide the original problem into at least 2. Notice that I'm not allowing much room for playing with the sizes of the subproblem. I'm saying if you divide your problem into B subproblems, all of them should be almost of equal size, N over B. Of course, in practice, doesn't have to be exactly equal. I illustrated merge sort on a list of size 8. And I chose 8 on purpose because 8 is a nice number. It's going to divide into 4 and 4. 4 is going to divide into 2 and 2. And then 2 is going to divide in 1 and 1. But if I have a list of size 13, I have to divide it into 6 and 7. And the 7 into 4 and 3. And the 3 into 2 and 1. So they are not going to always divide into 2 lists of exactly equal size. But they should be almost equal size. Okay? So this is why we divide it into B subproblems of equal length or almost equal length. We solve A of them. We have f of n for the merger. And we have a constant time for dealing with the simplest case of the problem. The Master Theorem says for this type of recurrence, and if the time to do the merger is polynomial in n, that can include constant, because if d equals 0, this is O of 1. If d equal 1, this is linear. If d equal 2, this is quadratic, and so on. The Master Theorem says if you have a recurrence of this form, and f of n is a specific type of function which is polynomial in n, then we can say that t of n can be one of these 3 explicit functions. T of n is either O of n to the d, or O of n to the d times log n, or O of n to the log of a to the base b, depending on these 3 conditions. So now you have the values of a and b and d, right? We have the values of a and b and d. We can check if a is smaller than b to the d or equal or greater. Depending on the value of this condition, you choose the one from here. And this is the Master Theorem. Of course, it's not an axiom of life that this holds. It is not a magic result. There is a proof for this. But the nice thing about having it with a proof is that once it is proved as correct, we can use it as a tool so that we simplify our life and make it much easier by taking a recurrence like this and in a very straightforward manner getting the actual function by just comparing 2 numbers, a and b to the d. Now let's look at the Master Theorem. Let's look at the recurrence that we got from MergeSort. First of all, we have to make sure that the recurrence we got is amenable to the Master Theorem. Okay, which means does the recurrence we get, does it have this form? The answer is yes. We have a equal 2, b equal 2, f of n is O of n, and c equal O of 1, c is basically 1. Is f of n O of n to the d? The answer is yes. In the case of MergeSort, n to the first, d is 1. So in the case of MergeSort, what is the value of a? The value of a is 2, because we solve both subproblems. What is the value of b? How many subproblems do we divide our problem into? It is 2. What is the value of d? How long did the algorithm take to do the merge? It is O of n. N to the d. Which value of d will give us O of n to the d? d equal 1. d equal 1. So now I need to look at a and compare it to b to the d. Right? So this is a, and this is b to the d. And I need to ask, is a smaller, equal, or greater than? 2 is not smaller than 2. It is not greater. It is equal. So I have this condition hold for MergeSort, a equal b to the d. Therefore, I get that t of n for MergeSort is O of n to the d times log n. And this is why MergeSort takes n log n time. Okay, so in this case we have in this example of MergeSort, we have seen divide and conquer, how we can take a problem, divide it into subproblems, conquer each one of them, and solve the big problem. We saw that such an algorithm is naturally implemented in a recursive manner, so that when you divide the problem into 2 subproblems, recursively call the original function on the 2 subproblems. We saw that for recursive algorithms, when we look at running time, what naturally arises is a recurrence. And the fourth thing we saw is that for these type of recurrences that we are seeing, instead of dealing with the full-blown power and complexity of recurrences and making our life hard, we have a special form of recurrences that are amenable to a very nice result, to the application of a very nice result that's called the Master Theorem, that without much thought I can just compare two values here, a and b to the d, and get the actual function. So I go from merge sort to this recurrence, from this recurrence through the Master Theorem to this value. Merge sort takes O of n log n. Remember that our naive algorithm, which takes elements and copy them to a different list, is O of n squared. O of n log n is better than O of n squared. Merge sort is O of n log n. The question is, can we still do better than this? Notice that merge sort, what it does, it compares elements, right? When we are doing the merging, it's comparing elements. So this falls into a category of sorting algorithm that is called comparison-based algorithm. It's an algorithm that when it's sorting, it has to compare pairs of elements, okay? One of the powerful mathematical results in the area of algorithms and area of sorting is that this is the best we can do if we employ comparison-based sorting approach. So if you look at any algorithm for sorting a list of size n, without putting any assumptions or constraints about the elements in the array, if it is doing comparison, the sorting algorithm cannot do n log n. If you see a sorting algorithm in the literature whose running time is linear, it takes O of n, then it cannot be a comparison-based algorithm. Okay? Or it can be wrong, of course, but if we assume it is correct, it cannot be a comparison-based algorithm. Okay? So for comparison-based algorithms that are comparing, like the first one we showed, O of n squared, where we always went through the list comparing elements until we got the minimum, that was n squared. This is O of n log n. We cannot do better than this as long as we are sticking to the comparison-based sorting algorithm. Okay? So merge sort takes O of n log n, and the Master Theorem allowed us to go from the recurrence to this explicit function that we understand how it grows. And this grows much better than O of n squared.